Hello guys and welcome back to the Maths and Physics blog. Today we're going to go over an example of our wave and optics playlist on thick lenses. So this will be a part, like the first part of two videos that I suggest you watch, the thick lenses and thin lenses, but this, you kind of need to know this so the second one makes a bit of sense. So this is the diagram we'll be using. This is actually part of the diagram we're using. It does change as we go along, but as you can see in the diagram above, we have an object on the left hand side. It is refracted through this lens, which has a radius of 5, and then it gives us an object. But one thing to note is that it's only from the left hand side that's been reflected. We haven't actually applied the right hand side refraction so far. So at the bottom we have our sizes. We have a lens of radius 5 we have a refractive index outside the lens of 1, a refractive index inside the lens of 1.33. Our object has a distance of 30 centimeters and a height of 1 centimeter. And one thing to note is that the object sizes and lenses have all been exaggerated in the size to make it easier. So how are we going to solve this? We're going to break this question up into two parts. The first refraction, so the image created from the first refraction, so the left hand side of the sphere, and then we're going to apply that to the second side, so the second refraction, so the image created from the second refraction, i.e. the right side of the sphere. So it takes the first refraction image, like the way the rays are going, and then it applies its formulas to that. So the first refraction, so this is the diagram we had at the start. So the figure shows the formation of the real image after the refraction on the left-hand side of the sphere. So using our sign rules, we see that C is on the same side as the outgoing ray, so we know that our radius, R, is equal to R1 and it's equal to 5. There's no negatives involved. And then using our equations for distances and lateral magnification, they have come up in previous videos, so if you want to learn about them, make sure you go back in our playlist. And then we we rearrange to get the distance of the image and then get the magnification. As you can see, the image distance is 40 centimeters away from the line it has been refracted through, and it has a magnification of -1. Thus, we see that the image from the first refraction is real, inverted, and at the same magnification. So now we're going to have the second refraction. So this actually takes the rays created from the first refraction, and then it sees what happens after that, as you can see in this diagram here. Now we need to consider one thing is the distance of the object. So the distance of the second object is equal to we need to think about the thickness of the lens. So we take the thickness of the lens and we minus the distance of the image created from the first refraction, if that makes sense. So we have our radius equals 5, so that means our diameter of the lens is 10 centimeters. And we know that our image created from the first refraction was 40 centimeters, and so we do 10 minus 40 to give us minus 30 centimeters. And then we also see that C is not on the same side as the outgoing light, as you can see in this diagram here. And so that our R2 equals minus R equals minus 5 centimeters. And then applying this to the equations we've got from before, we rearrange them and put our numbers in. We see that the image has a height of 9 centimeters. It has a magnification of 0.4. And what we do with magnifications, we can just times them together because they both apply equally. So then we get M1, which was -1, times M2, which was 0.4, to get the minus 0.4. And then this gives us the final image created from both sides of the lens, so the left and the right hand side. So this, from the object through the lens, we get an object which is demagnified, so it's smaller, it's real, so it does exist, the image we are seeing, and it is inverted, so it's upside down. So in conclusion, we can see that the image created from the object refracted through the thick lens is used by the equations for distances and magnification, and when we can also get these two equations here. But one important thing is I would suggest watching the next video in our playlist about thin lenses, because this takes these two equations and puts them in much more nicer form. Anyway, thank you guys for watching. I hope you liked this video. Make sure you hit like, subscribe, and I'll see you guys in the next video. Goodbye.